Uh, Great, so this is joint work with Eric Demain, Quan, Jason Lynch, and Virginia. Today we're going to talk about the I/O model and why reductions are really great in them. So first of all, the I/O model is attempting to capture the time it takes to take things in from your disk into cache. And as discussed, depending on which practical people you talk to, some of them will tell you that their bottleneck is really the caching efficiency. So for some algorithms and some settings, but that's what you really care about. So it turns out fine-grained complexity has been popular in the past few years. You've probably seen a million talks on the topic. And one of the things we're going to do is we're going to show how certain kinds of reductions can give you faster algorithms in the I/O model, even if they didn't give you a faster algorithm in the RAM model. We're also going to show that these same kinds of fine-grained techniques can give you some new lower bounds and explain why problems are hard from each other. And then lastly, we're going to sort of motivate caring about these fine-grained differences by the fact that a time hierarchy does in fact exist in this model. They don't exist in all models, but it does exist here. So let's start with some background. First, what is the RAM model? I'm going to be constantly saying that in comparison to being in the I/O model. Well, it's the standard model that you know and love. But just to be clear, you've got words of size W. Normally, we treat them as being log n bits in size. We get to do simple operations on these in O of 1 time, and that's the time we're counting. The simple operations are things like plus and times. And yeah, you're used to this. So what about the I/O model? The I/O model instead is going to be paying a lot less attention to the number of computes done. So you've got your CPU, you've got your cache, it's a bounded size, you've got your main memory of unbounded size. Your input has been written into this main memory, or this disk if you prefer to think of it that way. And we're going to be counting how many times we have to take things in from main memory into disk. So what's going on there? We're going to take contiguous sections of B words from main memory, and we're going to bring them from main memory into the cache. And in order to get enough space in the cache, we're going to have to write something out. And that operation of reading and writing is going to take 1 unit of time. So once things are in main memory, we're then going to be computing on them. So when we're computing on them, it's totally free. Why? Well, this is theory. We don't want to have to do things like care about factors of 100 floating around. Even if in practice, maybe the thing that people would want to do is like count exactly how many of these operations there are and multiply the appropriate values by 100. But instead, we're just going to treat these computations as free. So note that the number of words in the cache is m. So it's not the number of cache lines, but the number of words. The number of words in the cache is always going to be a multiple of b, so we have a nice integer number of cache lines in there. So we're going to talk a lot about graph problems. So I'm just going to quickly go over what graph problems we're talking about. There's all pair shortest paths, everyone's favorite graph problem. We want for all pairs of nodes to check the distance between them. There's radius. So for the radius of a graph is the node that minimizes the maximum distance from it. So this is a graph centrality measure. We've got diameter. You're trying to find the 2 nodes farthest apart from each other. So sort of a measure of how graph uncentrality, if you will. And then median, which is a different graph centrality measure where you're trying to find the node that minimizes the sum of distance to all other nodes. We've also got a bunch of matrix and array problems that we need to talk about. So orthogonal vectors. This problem, you're given 2 sets of n vectors. They're each of length a little longer than log n, say log squared n. They're 0, 1 vectors, and we want to know, are there 2 vectors that have a dot product of 0? Hitting set instead asks, can I find a vector in one of the lists that has a dot product of 1 with every single other vector? And finally, min plus matrix multiplication is the all pair shortest paths matrix multiplication version. And what you're going to do is you're going to basically take a list of distances and then find the two-hop path distance. So you're taking, for every row and column, you're asking, what various ways can I go, and tell me the minimum. So some background about running times. Also, throughout this talk, I'm going to be throwing tildes in front of things like O's and omegas, and what I mean there is that I'm going to ignore subpolynomial factors. So I'm going to be ignoring all of these logs. So there's a whole host of dense graph problems and min plus matrix multiplication, which can be used to solve them. And all of these algorithms run in n cubed over square root of mb time. And this might initially seem a little mysterious, but the key here is that these running times basically all come from the fact that if you take one of these problems and solve it with min plus matrix multiplication, that has a nice self-reduction. And then once you apply the Io-Master theorem, this is exactly the number you get out. Similarly, if you had a nice self-reduction for a problem that takes n squared time, this is the running time you'd get out. However, unfortunately, sparse graph problems don't get this running time for the most part. So we find that if you run your sort of favorite graph algorithm like breadth first search, you're going to do something like look at every single one of your neighbors for each of those nodes, look at their neighbors, and it turns out this looks a lot like random access and doesn't in fact do a nice job of finding contiguous sections in memory. Finally, when we get to matrix and array problems, we notice that we do in fact get this nice form that we were hoping for because it turns out they have nice memory locality. Great, so let's talk about how we get some faster algorithms. So first, what is sparse 2 versus 3 radius and diameter? What does that even mean? So given an unweighted graph, and it's undirected as well, we're going to be paying attention to graphs that are sparse. That is, they have nearly linear edges. So let's say n times log squared n. And the question we're going to be asking is the radius or the diameter 2 or larger than that? So note that these problems of 2 versus 3 diameter and radius, they're hard based on the orthogonal vectors conjecture or the Hiding set conjecture, respectively, in the RAM model. But the interesting thing about these is that the reverse is true as well in the RAM model, specifically for 2 versus 3 diameter, but not for larger values. So we have previously talked about the fact that this orthogonal vectors conjecture problem, we have an efficient algorithm for it, but diameter we don't, and we'd like to just sort of use this reduction and get a faster algorithm. So what are we going to do? Well, it turns out if we just wanted to immediately apply it, it wouldn't quite work, because it turns out it makes a ton of calls to breadth first search. And like a variety of other sparse graph problems, breadth first search is also extremely inefficient in the IO model. It should, morally speaking, run in n divided by b time, but instead runs in n divided by root b time. So we're going to need to replace this slow graph problem with instead some nice array problem. So we're going to instead be scanning arrays. But we will be using this other key insight, which is that diameter 2 versus 3 is really a set disjointness problem. So what are we going to do? We've got a graph, we've got nearly linear edges, and we're going to take every pair of adjacency lists, and we're just going to check if either they're distance 1 away from each other because they contain the other's node, or if they intersect on some node, and thus are distance 2 away from each other. So how are we going to do this? We're going to take portions of the list that fit into memory, and we're going to pay attention to one of these sections at a time, and then we're going to scan through the rest of the list to check whether these nodes are distance 0, it's a copy of yourself, distance 1, or distance 2. And for every single node contained in this section of memory, as we scan through, we can keep track of all these values. So we can, in fact, check, count the number of nodes at distance 0, 1, and 2 for every single node in this section. And so once we've successfully scanned through the list for every one of these portions, we can return these values. So this scan takes n squared divided by mb time, the time we were hoping for. And conveniently determining the number of nodes at distance 0, 1, and 2 from each of the nodes answers both the radius and diameter question. It's in fact more general, and we will use this a little bit later. So lower bounds. So there's a host of reductions. We just talked about a reduction that is meaningful in the RAM model, but wasn't initially meaningful in the I/O model. It had this piece in it that is as efficient as possible in the RAM model, but it turns out the notion of linear for the I/O model is different, and you have to be faster in order to be linear time. So it turns out there's also reductions that are meaningful in the I/O model, but not the RAM model. And sort of coming from the same point of view of, it turns out, these sparse graph problems often don't run as fast as they ought to, in some sense. And if you use something that's sort of faster than it ought to be to go between two algorithms that are slower than they ought to be, you can get a slower running time. But it also turns out that a bunch of these reductions just work in both. And you can connect a bunch of these dense graph problems to each other. We'll talk about that in a little bit. But first, so it turns out, using this counting mechanism of counting the number of nodes distance 0, 1, and 2 from every other node, you can use median in a sparse graph to solve the question of, is my radius 0, 1, 2, 3, or greater than 3? So 3 versus 4 radius. And the way you do this is you count the number of nodes at distance 1 or 2 from the nodes you care about, add a bunch of extra structure that equalizes this out, so you don't particularly care which nodes are at distance 0, 1, and 2, and only care about the nodes at distance 3 or greater, and then run median. But the problem we have here, if we try and use this same algorithm to say something about the RAM model, is that these running times are all n squared. And so saying, I start with a black box to an n squared problem, maybe I can solve it faster, and then I run an n squared thing. This is not meaningful. However, we get a full savings of m, whereas these problems are sort of slower than they ought to be. So it ends up being meaningful in the I/O model. So in the I/O model, these problems sort of have these running times that we've been able to achieve, and one can hypothesize that these are optimal, or you can not believe these are optimal, but simply want to know what's the network of reductions that connects these problems. And it turns out a bunch of the reductions that worked in the RAM model work directly. Some new things need to be created that potentially work in both the RAM and I/O model. Another thing to note is there are these reductions in the RAM model that go between problems that have different running times. A classic one is that you can actually solve the three-sum problem, which is an n squared time problem, with the zero triangle problem, which is a n to the 1.5 time problem in terms of its real input size, which is n squared, but an n cubed problem. So when you try and do something like this in the I/O model, the running times won't match up in terms of the savings and the cache size, because of the fact that the amount of problem you can solve while in cache for zero triangle is going to be n to the 1.5. If you could sort of solve a full n squared amount of work in your cache, a full m squared amount of work, you'd be able to get this full savings of m. But if you could do so, then you'd get a reduction in a direction that we haven't been able to do in the RAM model, which is a reduction that goes from a problem that takes a slower amount of time and solving it with a problem that takes a longer amount of time. So you get these mismatches here as well. Additionally, OV conjecture, reductions work. So the last thing is time hierarchy. So not in every single model do time hierarchies exist. For example, in various randomized models, these hierarchies don't exist. However, here, it is in fact the case that for every running time that's polynomially different from another running time, in addition to a factor of b, you do in fact get unique problems that are solvable in one and not the other. In the paper, we also explore generically like what problems are solvable with a polynomial number of cache misses, and how these connect to Turing machine simulations. It turns out improvements in Turing machine simulations of the RAM model will actually result in improvements in the necessary amount of savings you get in terms of the cache line when you convert problems from the RAM model to the I/O model. If that sounds interesting to you, I'm happy to talk to you more about that offline. So in summary, the I/O model is trying to capture caching, and we'd like to understand why some of these problems are fast and some of these problems are slow. And it turns out you can use these same ideas from fine-grained complexity to have a series of reductions between problems. Also, sort of looking at things from the perspective of fine-grained complexity helps explain why you get some of these running times in terms of n and b, and why they're consistent depending on what your running times in terms of n is. We get I/O-efficient reductions between problems, and another notable thing is people often complain that fine-grained complexity doesn't result in faster algorithms, and why do we always get lower bounds and upper bounds? And I'd like to say if you're working in fine-grained complexity and you're doing anything related to sparse graph problems, you should probably take a look at whether or not you're by happenstance getting improvements to I/O algorithms in the sparse model. I/O algorithms for sparse graphs are shockingly slow, and so you can often just sort of propagate some improvements there. There's a host of open problems. A lot of them are algorithmic. Specifically, I was just complaining that a bunch of these problems are very slow. One of the shocking things is even ST shortest paths in sparse graphs doesn't run in linear time in the I/O model. And I really think this should be fixed. Another thing is that there are reductions that you can have between these linear time problems that are completely not meaningful in the fine-grained complexity world because these problems run in truly optimal time. But because linear is different here, there can be meaningful reductions. So having better reductions between these would also help propagate in the improvements we do eventually get. Any questions? So we actually simulate a caching. We use a I/O model algorithm to simulate a Turing machine, and the Turing machine to simulate a RAM machine, and the RAM machine to simulate cache, and use that to get the hierarchy directly from the fact that there's a hierarchy between between different Turing machine running times. Yeah.